The next protocol, and really the last one we're going to talk about in the network protocol section, is ICMP, or Internet Control Message Protocol. Now, ICMP is something we've already talked about just to illustrate a few different examples already in the course so far. So we used some examples. We saw some pings when we were looking at IPv4 and compared those to pings in IPv6 and things like that. And that's certainly a helpful way to contextualize this. So you may already have at least a little bit of understanding of ICMP based just upon that alone. Now, as I mentioned, ICMP is really kind of a utility protocol. It's not really used to transmit data in a meaningful way. It's not an application layer protocol in that sense. It's used to service other protocols and service network administrators for a few different things. So one of the reasons ICMP exists is because it has certain features such as the ability to notify when a packet has expired in transit. And by existing, that means other network protocols such as IPv4, IPv6 don't have to build these functionalities in. They can actually rely upon ICMP to do that. So that's a nice interplay between those protocols. So ICMP is defined in RFC 792, so that's where you can read a little bit more about it. And one thing of note that I think is interesting here is some people will argue that ICMP is not really a network layer protocol. After all, if you saw the packets we've already looked at and the ones we'll look at here in a little bit, you see an IP header and then you also see an ICMP header. So ICMP is an embedded protocol, so you could say, well, in that case, shouldn't it be a layer higher? Shouldn't it be a transport layer protocol? And that's one of those things that goes back to the fact that the OSI model is really just a reference model and not always a perfect representation of all the data we'll see. You could argue that ICMP is a transport layer protocol, and I wouldn't fight you too hard on that. I think it fits better into the network section because it's used more with the other network-related protocols. It's more of service to those. So I look at it as a network layer protocol, as a layer 3 protocol. Some people will call it a layer 3.5 protocol. They'll say it kind of sits in the middle and it kind of strides the line between network and transport. Really, that doesn't matter. The OSI model is just a reference model to help us conceptualize these things better. As long as you understand how ICMP works, what it looks like, and so on, well, then you're really understanding the things you need to know about. Don't spend a lot of time thinking about where it fits in the OSI model to that degree. I just put it here because I think that's where it best fits personally, and I think it's the best place to teach it in this particular order. So as a utility protocol, it provides a few different features. One is the ability to check to see if a system is up. So a ping is something we've talked about, and a ping is actually a tool that describes an echo request and response, but that's one thing it will do. It allows us to trace the path along a route to a specific packet. So we talked about that when we talked about TTLs, and we'll show some more examples of that. It can also report path or packet transit issues. So if a packet expires en route, say the TTL gets decremented to 0, it can report that sort of thing about. And much, much more. There are quite a few different things that ICMP will do. We're going to do a brief intro here, show you the structure, go through a couple of the more common things, specifically echo requests and replies, and trace routes, and the ICMP responses that come back from that. So just enough to kind of get your feet wet, and I'll provide some forward lookups, some references to where you can learn a little bit more about ICMP to your heart's content. The ICMP packet structure itself is an interesting one because, for the most part, it's variable to the fullest extent. You see here we actually have 3 fields. We have a type field, a code field, and a checksum field, and the rest is variable. So that means it changes based upon the purpose and intent of the ICMP packet. So the type field is at ICMP 0 or 0 byte. The code field is right after that at byte 1 offset from 0. And those really, the best way to think of those is classification and subclassification. So the type is the classification of the message, and the code is the subclassification of the message based upon the type. So type and code are a weird way, I think, to name these, but that's what they are. But really just think of them as classification and subclassification. Now, what that means is that the variable portion of this packet, which begins at byte byte offset 4. That's going to depend entirely upon the type and code that are present. So from one type and code to another type and code, the structure will be completely different. It doesn't make sense necessarily for me to show you what the structure of every one of those could be, because there are just so many of them. There are quite a few types and codes. A lot of them are not really relevant anymore. Many of them were designed for the older days of networking when there were a lot of different issues that we didn't have to deal with now. But some of them are still important, and how they interact with different systems is important to know so you understand what normal ICMP looks like. All that said, there's a link on the screen to iana.org where you can actually look at the list of ICMP parameters, where it'll show you all the types and codes so you can learn what those are. So if you ever run into a type and code you don't understand, you can look up that list. Although Wireshark will also show you what those are, usually inline based upon data it's pulled from similar lists. So the key takeaway with ICMP here is that the type and code are the fields you want to look at, and based upon those, that will define what the rest of the variable packet structure looks like.